So here we are on the course map. This is Nate Fossey, and we're looking at our section right after the midterm, looking at problem set 6, but really focusing on module 6 right here. Sorry, it's module 7 and module 8. You see this one highlighted. This is the module we had right before the midterm, and we did not have homework for that. We did have quizzes. And here we have a problem set having to do with sampling distribution. And we're going to review some of the R code for that. And in the next 50 minutes or so, we're going to review some of that code. But essentially, we're going to look at these two modules in one go. And there's a lot of content here, so I'm going to go fairly quickly here. But I'm going to brush on the focus on the key elements. It's sort of, I would say, the broad strokes, the most important aspects of this analysis. What I want to emphasize here is that these two elements here, these two modules, are the beginning of this second half of this course, which is inferential statistics. The key word is inferential. Let's not overthink the term inferential, but let's understand what inferential means. To infer something, if you look at the dictionary definition of infer, what does it really mean? Well, I'll look it up right now and I'll tell you. If we look up the term infer, I'm going to open my dictionary app right here. From the Oxford Dictionary of English, to infer means to deduce or conclude something from evidence and reasoning rather than from explicit statements. From these facts, we can infer that crime has been increasing. I'm actually going to share that because it's terribly important for us to understand what it is that we're talking about when we think of inference. There's the term inference right here. The reason is that's all that we're doing. We're going to introduce a lot of new terms, a lot of new concepts. But the idea of inference is simply this, that we have data that we are describing, but we're going to make a larger conclusion beyond the data to infer some statement about the population. So in statistics, inference is to take evidence that we have and make a statement about the population. It's to take what we have and to basically make a statement about something larger. So in that sense, it's a very common term. You could think of, if you watch Sherlock Holmes, there's a TV show, Sherlock, that's pretty popular in British television. Sherlock Holmes is a detective who looks at evidence and infers or deduces, based on that evidence, something that is not explicit. That's all that we're doing when we talk about inferential statistics. We're systematically and principally making a statement about a population that we do not observe directly. And by population, I'm talking about everybody. I'm talking about a larger sample. And the reason we need inferential statistics is that it is too expensive, too difficult, too costly to sample an entire population. Often it is not even possible. So I think it's important to reference infer. If you look at the usage, there's a little comment on usage. There is a distinction between infer and imply. Imply means to subtly suggest something. However, Inferred means that something in the speaker's words enabled the listeners to deduce that this person was a traitor. So infer is different from imply because they're from different angles. The use of infer to mean imply is a common error. That's neither here nor there. But the point is, I might imply something, but you're going to infer it. Inferring is the tool by which you deduce or you conclude something based on evidence and reasoning rather than explicit statements. And in statistics, it's when you deduce or conclude a statement or a fact about the world based on evidence and reasoning rather than from an explicit total observation of everything. Because we can't do that. We can't observe everything. We can do the best we can with partial information. So I'm going to take us back to the course map. If we can go back to this, I'm going to try to share it one more time. I'm going to go back to the course map. Is this being shared? I don't know if I see that. Yeah, there we are. Okay, took a little while. Good. Thank you, thank you. So the basics of sampling and the idea of a sampling distribution, we're going to cover in one go. But this is where I want to take us, and I want you to see the bigger picture here, because this is going to tell you the so what. Because we're going to have some, if you combine these two modules into one, which is in essence the new terms and ways of thinking about descriptive statistics, and using those descriptive statistics to make an inference about a population that we don't have direct access to. That's all that we're doing. Then everything else, these tests for means, these tests for proportions, these tests for contingency tables and analysis of variance, and inferences for correlation and regression, 1, 2, 3, 4, these are analogous to previous modules that we had. Let me show you. When we do tests for means, we're looking at averages. We're looking at numerical data analysis, but we're going to try to infer from the descriptive numerical sample to the population. So when we look at the next module, think of it as a revisit of that third homework assignment, that third module, except with inference. When we look at the categorical data and we look at tests for proportions, remember a proportion is a percentage, or it is simply a probability. Regardless, a test for proportions is a test about in terms of categorical data. It's a test of categories. Say, is the category of a proportion of male and female, does that differ by religious denomination? Are women more likely to be Catholics versus Protestants, for example, in terms of the Christian faith? That's just an example. That's an example. That's an application of inferential statistics with categorical data. So we're just revisiting that. When we talk about contingency tables, a contingency table is also a probability table. Analysis of variance, we can just sort of scratch that out because that's a little bit extra, but it's basically the same. We have a table of categories. We have categories contingent on one another. So remember, if we looked at, in Module 4, we looked at probability of being in poor health, given that you live in poverty. Well, we're going to make a statement about whether or not those differences are statistically significant or rather just due to chance. And we're also going to infer whether or not those differences are true in the population. So we can think of our probability tables week and our week on relative risk in terms of inferences as well when we revisit it in terms of tests for contingency tables. And that's called a chi-square test. Now we're going to look at correlation and regression. We run out of time near this end of this term, so we can't have it in separate weeks. But look at this. our correlation analysis and our simple linear regression. Now we can think about correlations and regressions in terms of statements about populations. So for example, let's say we have a sample of 100 people and we look at height and we find that height is correlated with better health. Let's say we look at men. Is this true for all men? Taller men are healthier? Well, regardless of whether you use simple linear regression to look at the prediction equation or the simple correlation analysis, we're going to reinterpret or reanalyze, revisit those descriptive statistics so that way we can make statements about, we can make inferences to a population. So correlation analysis and simple linear regression are both visited in those 2 weeks. And then in the course review, I'm going to preface this for those of you concerned about the midterm. The course review will cover these elements here, but it will also cover the descriptive statistics. So the course review will give us everything, and that's in preparation for the final exam. And by then, you're going to be very well equipped to interpret both descriptive and inferential statistics using the core tools and techniques. But I want to assuage you a little bit by emphasizing that these tests for means is simply the application of numerical data analysis by making inferences. When we can analyze categorical data and make an inference about those categories, we can look at contingency tables or probability tables and make inferences about those. We can look at correlation and make inferences about those, regression and inferences about those. Okay, and in all of these other modules, we're going to revisit some key elements, some key terms, and that's what we're going to go to next. So let's go to the readings now. And I want to introduce to you some terms. These are all from Chapter 4 of the Open Intro Stats book. And I'm going to skip over some points, but I just want to give you some highlights of where to read this and what terms to burn in your brain when you look at analyses. So let's see if I can do this. Open Intro Stats, share screen. This week is called the Foundations for Inferences. What they say in the first sentence of this, I think, is crucial, which is that statistical inference is concerned primarily with understanding the quality of parameter estimates. That sounds like a lot of jargon here. Let me see if I can hide the sidebar. All this is saying is a parameter estimate is simply our best guess from the descriptive sample. And statistical inference is a way of us telling us how close are we, how likely is our sample to be descriptive of the population. I'm going to skip over these parts and we're going to introduce some important terms. The first term I want you to know is, and that we review in lecture, is this idea of a point estimate. A point estimate is simply a sample descriptive statistic. Okay, so it looks like we might have some internet quality issues. We'll see if we can keep that okay. So when we look at the sample mean, say we look at numerical data analysis, here we have an example of the average of heights in some survey. We don't need to know what that is. A point estimate is our description of our sample estimate. And when we take our sample estimate, our sample mean, we're going to call it a point estimate when we want to make that sample mean, when we want to infer from that sample mean to the population. Typically, the notation in statistics is that population parameters or population means or descriptive population descriptive statistics, those are in Greek. Sample descriptive statistics are typically italicized algebraic symbols. So here we have something called X bar. See that X with a line on top? That means that's the average. That's the sample mean. Now, if we're just to use the sample mean to use it as a descriptive statistic, then we would call it simply a descriptive statistic. But if we want to make a statement about a population that is unobserved, then we'll call that sample mean the point estimate of the population parameter mu. Mu is the Greek letter for m, and that is typically conventionally used to describe the unobserved population mean. Now, here's the deal. We're going to talk about something called sampling variation. Let's say you take a sample of 1,000 people and you get an average height. And then I take a sample of 100 people and I get an average height. And they're both different. That's what sampling variation is. It is simply when you take a random sample of a population and re-estimate that sample, it's going to vary. They're all going to be pretty close, but they're not going to be exactly equal to the population. Well, what do we do about this? I have a point estimate, you have a point estimate. Let's assume that all three of us have, 10 of us have point estimates. Well, the good news is, and those are some descriptive statistics, the good news is that while point estimates are not exact, as long as you take a random sample around an n of 30, that is, as the sample size increases to about 30, you're going to see that our accuracy of something like an average of height, our point estimate is going to approximate the true population mean. 30 is about the lowest, but depending on how large the population you're inferring to, and depending on the variability in the estimate itself, the sample size may differ. But the main crucial point is, and I'm going to zoom in on this figure, the main crucial point is, as sample size increases, our accuracy of our point estimate also increases. And our minimum threshold is going to be about 30. But as you can see here in this example, this is the running mean of student height in meters. I think it's a little confusing when they call this the running mean. All they're saying is that let's assume we take a sample with 0, okay? You're going to have a 0 value for average height in meters. But then you take another sample and you say 5 people. It's going to be a little bit higher than this little dotted line. This dotted line is the true population average. But as the sample size increases, you can see that you have some variability around 10 or 20. It's a little bit off. It's a little overestimated. Then our sample's a little bit too high. But then you start seeing diminishing returns in this particular case, so that as you increase your sample size, at some point, your estimate is going to be good enough. I don't know if I'm highlighting this. I'm going to actually annotate so that way you can actually see this. So if you can see about a sample size of about 30 right here. I don't like that drawing right here. I'm gonna stop the annotate. I'm gonna clear my annotation here. What I just wanted to show is actually, I'll just spotlight. What I want to show is that if you have a sample size of, say, 25, you're going to have something a little bit above the true population parameter, mu, that is unobserved. But when you get around to, say, 30, you're pretty close. In fact, you're right on the nose around 50, but you're going to see some uncertainty regardless. But the point is, it's going to cost you twice as much money to have a sample size of 100 as opposed to a sample size of 50. And what gain do you get from that increased sample size? Well, nothing really. You're still going to have some uncertainty in your point estimate, but you're still going to be able to make an inference that is used evidence and reasoning to make a statement about the population that is going to be relatively close, yet at the same time have some kind of uncertainty. And the point here is, while the sample size itself may need to be larger depending on the study or the precision that you're looking for, regardless, there is a point of diminishing returns after which you do not gain as much from increasing your sample size. To give you an example of very common use of inferential statistics, if you look at if you look at election polls, presidential approval ratings in the United States, you'll see that these often have about a sample size of about 2,000. Some of them will have smaller sample sizes, maybe 500. And then they'll have something called a margin of error, which we'll talk about. But the point I'm making is that you can take with a simple random sample, that is, you take a random sample of Americans in the United States, you can take a sample of 2,000 people and make an estimate of what the true population parameter is for a country of 330 million people. That's pretty remarkable. And that's really cool. Now, of course, the point estimate is always going to be uncertain. It's always going to be variable, no matter how large your sample size is. And this is where we get to this idea of when we get to confidence intervals. And to understand confidence intervals, we want to talk about the standard error of that mean. Now, this is another term that might sound a little confusing, because it's an error we think of as something as a mistake. Standard is something that is standardized. But all we're saying when we talk about standard error is that if we take a sampling distribution, that is, if we take if we aggregate, let's just imagine in this hypothetical case, we take 100 different studies, 100 students in the class, each take a simple random sample of the average, say, what was this, height of students in meters. And then we have those averages. Those averages are the sampling distributions. It's hypothetical now, but we could actually do this in practice. 100 students taking 100 different separate studies, and we average those. And then the standard deviation of those averages is the standard error. I know this is not going to be totally clear, but all we're saying here is, if we repeated this study, whatever it is, say we did a sample of 100 students and looked at their height, the standard error is, on average, what is the average, let me see if I can say this. What is the average, on average, how much do students vary from sample to sample in their estimate? So on average, how much does the point estimate differ? That's what the standard error is. It's sort of, on average, if we did 100 different samples or 1,000 different samples, on average, how often would our point estimate differ? That's what the standard error is. In descriptive statistics, we talk about the mean and the standard deviation. Okay? In inferential statistics, we talk about the point estimate and the standard error. The point estimate is our best guess. The standard error is, on average, how much does our best guess vary? Here's an example of a sample mean with a point estimate and some variation with a sample size of 50. They talk about a sampling distribution. I guess I could read this to you, but I want to go to the standard error of an estimate first. The standard deviation, this is better ordered. The standard deviation associated with an estimate is a standard error. It describes a typical error or uncertainty associated with the estimate. And the way we estimate a standard error is a really cool concept, which is that this idea of basically the central limit theorem. But before we get there, we can look at this equation right here. If we want to know on average how much does on average how much does a point estimate vary, we can estimate that by using sigma, which is the population standard deviation divided by the square root of the sample size. Now, we're not going to observe sigma, so we're going to estimate that with the standard deviation in our sample, because we're not going to know sigma rather. But this is what's really cool, which is it goes to this idea of the central limit theorem. I'm sorry, I'm going to skip ahead because will it tell us what the central limit theorem is? Well, it doesn't. I'm looking for the central limit theorem because this will explain to us how it is that we can actually make an estimate. Here we go. The reason we can basically make an inference is that if we take a bunch of different samples, then we can know that the average of those samples are going to be normally distributed. So there's the informal description of the central limit theorem. If a sample consists of at least 30 independent observations, right, we just take a random sample of 30, and the data are not strongly skewed, then the distribution of the sample mean is well approximated by a normal model. This means that if 100 students in the class each do their own study and do a random sample of 30 people, the distribution of those averages is going to be normally distributed. It's going to be a bell curve. And that's why we can make systematic inferences, the central limit theorem. If we can go to I'm just going to take us to the sorry if I'm moving ahead. I just want to show you in the course lectures this idea of the central limit theorem. This is worth reviewing. This is I want you to know what slide this is. Slide 32 of this week. Keep this, save it for your notes, make a mark of this. Remember X bar, this is going to be our point estimates. This tilde here is mathematically a way of saying the distribution of our point estimate is a normal distribution that is a bell curve with a true population parameter with a true sigma squared divided by our sample size. This right here is just that standard error that we talked about. Sorry, sigma. I'm sorry, you might not be able to see it. Sorry, I need to reshare. Okay, now you should be able to, can you see this now? Good, okay, you should be able to see slide 32 of the lecture. Thank you. So we talked about point estimates. We talked about standard error, which is on average, how much do we expect the point estimate to vary? And then we talk about how we can conclude that the standard error is always going to be the standard error. And that's because of the central limit theorem, which states that if a sample size is 30, consists of 30 independent observations, if we can describe the, and if we do this many, many times, it's going to be normally distributed with population parameter mu and characterized by a variance of sigma squared over n. Remember that sigma divided by the square root of n is the standard error of the mean. I'm going to read this slide to you for emphasis. The CLT, central limit theorem, states that if random samples of size n, typically 30, are repeatedly drawn from any population with mean mu and variance sigma squared, which we don't know, then n is relatively large, n equals 30 for most distributions. The distribution of these sample means is approximately normal. The distribution of sample means of size n drawn from the same population centered around mu and has a variance of sigma squared over n. Then it goes further. The distribution of sample means is symmetric and mound-shaped. It's a normal distribution. This is very cool. I'm going to show you from the homework what this looks like. Because other than memorizing that this right here is a standard error and that this right here characterizes the central limit theorem, it is imperative that you understand and see for yourself how the central limit theorem works. Fortunately, we can do that with the homework assignment in problem set 6, where we have a sample of Iowans from the Iowa Census, and we're going to go to that. And I hope I'm not switching too much, but I think it's beneficial to switch systematically so that we can understand, because some things you learn by doing. It took me a long time to learn how to learn some of these issues. It looks like I might have lost that screen share, so I'm going to stop it and I'm going to try to share it again. We're going to go to the RStudio console and we're going to look at the script for the homework this week. And I made some edits to the line, but if you look at the end of this, you can see something called visualizing the central limit theorem. I'm going to remove some of the plots here. I'll just clear all those plots actually, because I don't want to confuse anything. And I'm going to clear the console itself. And here I'm going to do Command L, or sorry, I think it's Command Return. Oh, I actually just ran the code. Okay, good. Let's get rid of that code here. What I want to show, first of all, is if we look at the Iowa Census, look right here, you'll see that the census consists of 55,000 observations with 5 variables. Now, there is a census. Typically, the census in the United States is done every 10 years. It's quite expensive to do. And quite often, because it's expensive, you can't ask that many questions. What we're going to do is we're going to take a random sample of that census. I actually I'm going to remove some of these. I want to remove the samples. And I'll show, what we're going to do is we're going to first take a look at the population parameter, but then we're going to look at what happens when we increase the sample size and when we average those samples. So first of all, let's just take a look at the mean of the Iowa Census. So I'm going to actually scroll up and we're going to look at the population parameters. Typically, you can't see this, but we're fortunate enough that we can see that here we have an average in terms of education. Let's see what the education variable is. It looks like it's some numeric years. It might be years of education, say after kindergarten. I'm not really sure. Regardless, our education variable is 6.98 in the population. In the real world, in most of life, you won't know what that is. But here we're using an example of a census where you know the average, our population parameter, and we know our population standard deviation, that's sigma, and this is mu. We know those now, and we're going to look what happens when we take different kinds of random samples. So if we take a random sample of 10, let's pretend like we didn't have very much money, we just only had 10 people, and we're going to take the average of that. What do we have? Well, look, we have an average of 5.1. That varies quite a bit from I'm sorry, I got a message here. I didn't mean to do that. We have a sample that is, we have a mean that is quite different. And now what we're going to do is we're going to actually do another one, and we're going to see how much that varies. Well, there's another random sample. Okay, that varies. Let's do it again. Let's imagine we have 3 students each do a sample. Okay, by the way, this is going to differ whether or not you do it or I do it, because I have not set a random seed, which means that we can replicate this. This is totally random. These are just like flipping cards. The point is, we have an estimate that jumps around our true population parameter of 6.9, basically 7. They're all kind of close, actually. For a sample size of 10, you're still pretty close. But 8.6 differs quite a bit from 5.1, and those are consequential. If you notice, that's because we've set our sample size to 10. Now, imagine we had 500 samples. We have this little do function here, which means we're going to repeat this 500 times. And we're going to take our samples of 10, and we're going to look at what happens when we take 500 samples of 10. Okay, that's where we did it right there. This is we just created the Iowa 500, and we're going to take the average. Well, first we're going to graph those averages of sample sizes. Look at what we have here. This looks like a normal curve, and in fact, it's pretty close. And if we take the mean, even with a sample size of 10, we have a point estimate that's pretty close to the population. Remember, our population parameter was 6.99. Here we have something that's 6.8. And then we have the standard deviation of our estimates, and this is the standard error. It is the standard deviation of the mean of our sampling distribution. So what we've done is we've created a sampling distribution. It's a distribution of samples. And then we take the mean of that sampling distribution, and that's our point estimate. We take the standard deviation of those means of our sampling distribution. That is the standard error. The mean, so again, if we take a bunch of samples and estimate the population mean, for example, the average of those, the distribution of those samples is the sampling distribution. The mean of those samples is the point estimate. And the standard deviation of those means is the standard error. And that is roughly bell curved. I'm going to do this again just to show you that even when you run this, you'll still see some variability in our sampling distribution. Here we have a point estimate of 7, and we have a standard error of 1.24. This is because we have small sample sizes. We're doing 500. And as we saw before, when we looked at the running average of student height, for example, in the textbook example, we saw convergence after a certain sample size. But here we have a relatively small sample. What I'm going to do is I'm going to increase the sample size to 30, and we'll see what happens. So here we're going to estimate we're going to do a sampling distribution of education and look at the point estimates and the standard error when we have a sample size of 30. Here, we're much closer. We have a mean that is very close to the point estimate. We also see something else interesting, which is as the sample size increases, our average of the means shrink. This is a good thing. The smaller the point estimate, it means there's less variability in our sampling distribution. It means that we have a more precise estimate. Of our population parameter. We have a more precise estimate of our population parameter. So our standard deviation of the means of our sampling distribution, ideally, in a census, would be 0. But that's never really going to be the case. But as our sample size increases, we see something smaller. And we see our point estimate already with a sample size of 30, consistent with what we had talked about earlier. We see our point estimate being pretty close, but we're still going to be uncertain about it. But we see that shrinking of that sample size of the standard error, which is a measure of uncertainty of our point estimates. We see that shrink as our sample sizes increase. Let's do this again. Again, we have a point estimate that is really close to 6.99. See, notice it varies now in the thousandths decimal place. We have 6.96, 6.96, and we see our standard error right around 0.7 something. And that's only by increasing the sample size from 10 to 30. We're going to do this now as we follow the homework. We're going to increase our sample size to 100. What do you think is going to happen? Well, we're going to have my guess is we're going to have, if we're going to look at a sampling distribution of 500 samples and we're going to have a sample size of 100, we're going to have a point estimate that's basically the same as the population parameter. And we're going to have a standard error that is the average of our sampling distribution, the average of our means, the standard deviation of our means of our sampling distribution. It's going to shrink, but it's not going to shrink as much as we'd like it to. Because remember, as we saw before, when we looked at running averages, you see convergence of, we see increasing precision, but you're never going to get to 100% precision. You're never going to decrease that standard error to 0 unless you have the population. But let's take a look at what happens. I'm going to guess we're going to probably have 0.6 for our standard deviation of means of our sampling distribution. Okay, it's 0.4. That's better than I thought it would be. But look at this. If you notice what happened with our point estimates, our point estimate's not that much better, but we have a smaller standard error. And this goes back to the point I had made earlier, which is that precision is overrated. I talked about this maybe in the first lecture, because when we talk about inference, our point estimate might jump around, but it's going to be estimated with some variability, some margin of error, some degree of confidence. And even though our point estimate is a little bit off here, more off than, say, if we had a sampling distribution with sample size of 30, we have a smaller standard error when we increase our sample size to 100. Let's do this again, just to see what happens. Now we have a point estimate that's actually pretty close to the population, and you have a smaller point estimate. So as you can see, sampling distributions vary, but they have some interesting properties, which is that as long as you take random samples, the larger the sample size, the smaller the average of the point estimates will occur. And no matter how large you get, let's even make this larger. See if we even do that. Well, I'm going to increase this. We'll increase to a sample size of 1,000, and we're going to, yeah. Well, if we do a sampling distribution of 1,000, we'll see what happens. You get something really close to the sample, to the population mean, and you have a very small standard error. And our standard error is on average, how much would we expect our point estimate to vary if we had X number of samples. Here we have 500, but this is pretty arbitrary. We could do 5,000 samples. It's just going to take longer. It's going to take 10-fold longer. We'll see if that works. I want to take us to, we're going to skip ahead. I want to take us to the sampling, an illustration of the essential limit theorem. I'm going to actually stop that because you can see that this is normally distributed. Just look at these. There's some variation here, but that's pretty cool. You take the average of samples, random samples, above n 30, even with an n of 10, they're going to be approximately normally distributed. Let's take a look at this here. Okay, we're going to take a random sample and calculate the sample mean. Now we're going to do this, take this and take a look at it 5 times. So here we have the 5 means. And now we're going to draw a random sample of size 10 and calculate the mean of a numerical variable 500 times. And we're going to graph the resulting distribution of sample means. And now we're going to overlay what we've just done with a normal distribution model. Remember, the normal distribution model is going to be that bell curve. It is symmetric. It is not drawn from the data. It is hypothetical. And look at that. That's beautiful. That's essentially what you do. And we can do this as many times as we want, and you'll see some variation. But that's going to be basically the bell curve. And that's what the central limit theorem is. You take any sort of samples, and it doesn't matter the variable. We know something about what would happen if we took, say, 500 samples or 5,000 samples. We know that it would be approximated. We know that our point estimates can be described in terms of one estimate in a hypothetical distribution of samples that are bell curved, that are shaped by the bell curve. Well, now what can we do? Well, we know, go back to that equation for the bell curve, and we know that we can take the sampling distribution of we can estimate the standard deviation of the sampling distribution based on its population. So, we take a, if we go back, where are we? Sorry. Yeah, if we go to this point right here, the main point of the central limit theorem is now, because our sampling distribution is approximated by the bell curve, the sampling distribution of sample means can be approximated by that normal distribution model. So now, with just one sample, not 500, we can now give our point estimates, and then we can give our best guess at the standard error based on our sample size. And we do this by taking our, if we look at the equation from the reading, it's sigma divided by the square root of n, and the square root of n is our sample size. So we take our sample standard deviation, which is our best guess at the population standard deviation, and we divide it by the square root of our sample size. And here's some examples here, but basically, if we take the mean and the standard deviation of our education variable in the population, there's our mean and our standard deviation of education. Remember, the standard error is an estimate of a precision of the point estimate of the mean. The standard error is not the standard deviation of that variable. To estimate the standard deviation of the sampling distribution, what we're saying then is we're saying this is the standard error, which is the standard deviation of the sampling distribution. That's different than the standard deviation of the variable. This is a statement right here that the standard error is our measure of precision of our point estimates. The standard deviation of sampling distributions refers to the point estimates. Because remember, our sampling distribution only describes means. So this tells us, on average, how much does our mean vary. So really, it might be a little confusing to even include that. But notice what I did here. You don't even have to run simulations or samples. You can actually, the only information you need is our sample, sigma, and we just need the square root of the sample size. Now, there's something about a normal distribution, because we can, with the central limit theorem, we now have one bell curve to describe the sampling distribution. We often call this the standard normal distribution model. Standard meaning it's across many different kinds of samples. Normal because it is, not because it is normative normal, but because it is bell curved. Distribution model because it's based on a hypothetical number of distributions. And these have basic characteristics. The graph of the standard normal distribution model can be run by using this code, using the plot dist function, but it is characterized as having a mean of 0 and a standard deviation of 1. This means that a 2 in our standard distribution model means that we have 2 standard deviations above the mean, a negative 2 is 2 below. And this is where we get to the concept of z-scores. Z-scores are the formulation of means and averages to the standard, to each average within the normal distribution model. And so when we talk about questions having to do with, say, if we have Daryl's age of a z-score, and we know his age is approximately a normal distribution, what is his percentile? We can know what percent you are above someone else. You can know where two people compare based on their z-score. The main point here is if I have a z-score of 2, then that means I am about 2 standard deviations above the mean of 0. And because I'm 2 standard deviations above the mean, and because we can assume the standard normal distribution model, we can look at the area under the curve. And the area to the left of me is the percent of people, say, below my height. Let's say my height, because I'm pretty tall. I'm probably around, I have a z-score of 2 probably. About 2% of the population is taller than I am, but 98% of people are shorter than I am. And that's what my percentile is. A percentile is, given your z-score, or given your position in the normal distribution model, what percent of the population are at your score or lower. So that means if we have a percentile, and we assume that the distribution of heights, for example, which is true, is normally distributed, we can take a percentile and transform that to a z-score. We can also take a z-score and transform that to a percentile. We can also take 2 different scores from 2 different tests, as we have shown in the module, look at those z-scores, and then compare percentiles based on different metrics. I'm not going to go through some of these examples because they're pretty clear here, but the main point is that's what you can do with the normal distribution model, and that's separate from statistical inference. Basically, the central limit theorem is crucial toward understanding statistical inference, and it has to do with this concept of sampling distributions. And what we reviewed, we reviewed the three concepts. We reviewed this idea of point estimates, right? It's our best guess of what the average is. Then we looked at our sampling distribution, and we showed that a sampling distribution is basically normally, we described what it was, which is sampling distribution is the distribution of our point estimates or averages of samples. And then we show that it is approximately normally distributed, is normally distributed if n is greater than or equal to 30 or so for each sample. Then we talked about the standard error, which is basically your sigma divided by the square root of our sample size, which means that basically if we take any study and we know our mean, and we can basically approximate sigma, the population standard deviation, and we can estimate the variability in our sample using our sigma, our sample standard deviation. So we can actually do sample standard deviation divided by the square root of n of our sample, and that'll tell us conceptually, on average, how often would our point estimate vary. And what we learned was that we can have the same equation, simple equation for the standard error, because our distribution of samples is normally distributed, and we call that normal distribution, that property, the central limit theorem. And the central limit theorem we can also translate in terms of characterizing values within the standard normal distribution. So the central limit theorem is simply a statement about the properties of sampling distributions. This is actually, we can actually encapsulate this here. And the second point, which is that the central limit theorem is the fact that sampling distribution is normally distributed, even though point estimates vary. And the standard normal distribution is simply the normal distribution, or bell curve, with mean 0 and standard deviation of 1. And then we can characterize values as z-scores, percentiles, and compare values or positions with different metrics. And I should actually say at the beginning of this, not to forget this whole big picture, we talked about this idea of inference and what inference means. And from here, these points are not to be forgotten. We're going to review these. We're going to revisit these again. But the point is, when we talk about inference, we can use the central limit theorem. We can use these concepts, and we can make a statement about our sample and describe our accuracy of our point estimate within something called a confidence interval. And this is something I didn't really get to. We're running out of time, but the confidence interval is simply our point estimate plus or minus 2 times the standard error. It's 2 times the standard error because I'm going to show you, look at this right here. If we look at the standard normal distribution, remember 1 is the average of our point estimate in our sampling distribution. 2 is 2 times the standard error. If we look at that area under the curve, plus or minus 2, we're talking about a big chunk of that bell curve. So our confidence interval is a statement about our interval, our degree of precision of our point estimate in our sample, given our sample size and this really cool property of the central limit theorem. Now I'm going to see if we even have a. I'm going to see if I can graph that. But the main point is our confidence interval is something that is important for us to look at and to consider, because I'm actually going to move to I want to take us to I do want to end on the confidence interval because it is important. We're going to revisit it, but our confidence interval is again derived from our standard error and our point estimate. That's all it is. And a confidence interval is our degree of precision of our point estimate. It is nothing more than that. It tells us how, literally, think of the term confidence interval. It doesn't tell us whether or not the true value lies there, because we can have values that lie outside of the confidence interval. But it does tell us what's our best guess. And as we saw, our standard error, when I talked about how small the standard error was, a smaller standard error is actually a smaller confidence interval. So I'm going to take us to, you should be able to see this. I don't think if you do, but I'm going to resume the share. No? Okay, I'm sorry. Stop the share. I'm going to re-share this, the Open Intro Stats book, because I think it has a good example of confidence intervals. Basically, if we look at our confidence interval, we have 1.96 times our standard deviation, plus or minus. Basically, all we're saying is, and this is page 177 of Open Intro Stats. We're saying that our convention is to say roughly 95% of the time our sample estimate is going to be within 2 standard deviations of the mean. And I said roughly 2 because it's technically 1.96. But to visualize this, take a look at our normal distribution. We typically use the 95% confidence interval. This is the normal distribution. What we're saying then is, let's take a look at our example of, say, we'll look at education in Iowa. We had a point estimate of, say, 6 something. Then we had a standard error, and our standard error would be characterized as 1. And our degree of confidence that we often use in science is 2 times the standard error. So the smaller the standard error is, the smaller the confidence interval is, which means that basically we're more confident in our estimates. But we use this 95% confidence interval because it's a compromise between something like the 99% confidence interval, which requires more data, more information, and something that would be, I don't know, the 68% confidence interval, which would be within 1 plus or minus 1 standard error. 95% of the confidence interval says if we do a sample, say, of height of students, and we take an n of 100, and let's say our height of students is, I don't know, 5.5 feet. Our 95% confidence interval says if we do that, redo that sample 20 times, 19 out of those 20 times our true population height will be within that 95% confidence interval. So it tells us something hypothetical about our point estimate, but it does not tell us whether or not our actual sample estimate is true. This is why statistics can get things wrong. It's not a problem with statistics. It is simply the fact that when you make an inference, just as Sherlock Holmes is making an inference, he is not looking at every bit of data. Now, of course, Sherlock Holmes is fictional and always gets everything correct and right. But in real life, we're never 100% confident with our point estimate. We can say 95, and if we were to run this 20 times, our true population mean will be within this confidence interval. That's all we can say. We cannot say whether or not our particular point estimate is in fact within that confidence interval. And that's when we get to hypothesis testing, which means that we talk about certainty. And sometimes studies are wrong, sometimes they're, but that doesn't mean that the study was incorrect. It just means sometimes you can have a value that lies outside of that 95% confidence interval. If you look at interpretations of confidence intervals, and we talk about hypothesis testing, I just want to show you something else here. We talk about things called p-values. I want to show the long range of, sorry if I'm skipping ahead, there's a lot here, but I want to show to you well, we already looked at this. The larger sample size, the more our point estimate becomes more normal. We showed that earlier. But I wanted to show what happens when you look at many different confidence intervals. And I'm sorry for skipping ahead, if this makes you dizzy. That would be from the lecture. I'm sorry. It was. Remember our if you can see this, I'm going to stop the share. I know I'm going over about 15 minutes over, but I think it's important to review this so that students know what the confidence interval is. A confidence interval provides additional information about variability. So we have our point estimate, we have an upper level and a lower level limit. And if we look at this Iowa data points, our point estimate is about 2 times the standard deviation plus or minus. This is what I wanted to show you. Here we have our sampling distribution of our point estimates. And here are 100 confidence intervals based on this, which means that if we're to do this this many times, we'll see that sometimes we might not actually have the true population parameter within our confidence interval, but most of the time we will. I don't think you can actually. If I want to annotate, I don't know if you can see this. Can you see my? Oh yeah, you can see this. Good. I just want to highlight. I want to just mark up. Well, I can't. What I wanted to show you, if we can look at this. Oh, but yeah, the point here is that yeah. Here's the key point. Some of our confidence intervals capture the true population mean, the vertical solid line, that's what that is, while others do not. Some intervals do not contain the true population parameter. And we don't, and additionally, when we do a study, we don't know if ours actually includes the true population parameter. We just have a degree of confidence. I think of it, an analogy would be to think of inference as a statement of our best reasoned guess, a principled estimate. So we call it a point estimate. A point estimate means it's one number. Estimate refers to that probabilistic statement. But I was going to say it's analogous to making claims about the weather. We can do a weather forecast, We can say we have a chance of rain, but if it doesn't rain, that does not invalidate the methodology or the tools used. And yeah, I think that's important here. But the main point is conceptual. So if we think about what does this confidence interval really mean, our confidence is in the process of constructing the interval, not in any one interval itself. Thus, we expect 95% of all 95% confidence intervals to contain the true population parameter that they are estimating. In other words, if we did 100 of those, 5 of those confidence intervals will not include the true population parameter, but 95 of those will. That's what it really means. So I think that's all we need to say here, except here's an example of a sample that might not include our true population parameter. So I'm glad we ended on confidence intervals, because that's really crucial toward interpretation for everything else that follows. When we talk about tests for means, we're going to look at population means and compare our sample mean to the population to see whether or not our mean in the sample is consistent with our hypothesized population. We're going to look at means to see whether or not two means differ by categories, to see whether or not those means actually differ, as whether those differences in means between two groups is by chance, or whether or not those differences in means are true within the population. We're going to make the same claims about proportions. So the proportion of say, women who go to church versus men who go to church, is that difference true in the population? When we talk about correlation, we're going to have constructed a 95% confidence interval around a correlation. So if we have a correlation of 0.5, what is the point estimate for that correlation if we had the true census or the population? And then finally, when we talk about linear regression, we're going to talk about our slope and our intercept and interpret those in terms of 95% confidence intervals and statistical significance. Statistical significance simply states that we can make a claim that there is a difference beyond chance. Statistical significance and practical significance is what we're going to revisit. We're going to emphasize more of that next week. I know this was quite a bit of material. I hope it was helpful. I think it's important to revisit these, and I'm just going to end on the course map just so you have an idea of what I was saying before, which is these tests right here. When we talk about tests for hypotheses and other kinds of tests for inferences, we're just building on these ideas of the central limit theorem and of the properties of samples, the properties of the sampling distribution, which are the fact that they are normally distributed, and that we can characterize them in terms of a confidence interval. Thank you very much. Thank you for your patience, and thank you for letting me go a little bit over today. I hope that was helpful.